Thank you. We are solving systems, and in many cases we encounter linear systems, but we will also learn about nonlinear cases. And let's briefly review linear system. Linear system has x1, x2, and so on terms with appropriate coefficients, and the method that we developed was iteration stuff. And then by using iteration, we can initially guess the solution. x1 is, for instance, 1, x2 is 1, and so on. So we guess the solution. And then using these input, we determine new x1 by this relation. This gives us x1 relation. So from this we can find the x1 relation, and so on. So last time we solved an example, and today let's solve one more example. So I'm making up a problem. So let's consider x3 equals w times 7 minus 3x 2, 1 and 3, right? And then 1, x1, and then plus x3, x2, and then divide by some number such as this one. So we solve the system this way. So here we represent the equation using this times x1 equals this number minus the sum of this thing. Then we can divide by this number to get x1. So I did it. So x1 equals something like this. And then by using weight, we can write it this kind of way. And if you have any questions up to this point, you can ask me. Because last time we covered it, I do not explain further. And then let's run it. So initially, with w equal to this number, we get these things. And then we run it, and then run it, and then run it, right? So we run and run and run. So it's iteration, right? So x1, x2, x3 were used here to determine new x1, x2, x3, and then we do these things. And then this w can be changed. W can be between 1 and 2, and if this 1 is called Gauss-Seidel method. If it is between 1 and 2, then it's called SOR, successive over relaxation method. So as I mentioned, this W determination is trial and error. What best works for the given system may be chosen later. So we covered everything up to this point, and if you have any questions, ask me. If you don't, then I will mention about nonlinear system and then cover interpolation. Great. Then nonlinear system has some powers, or the multiplication like this, right? Then it's nonlinear. It's nonlinear, right? So when you have these kind of things, how can he solve the equation? That is the task. Then we need some kind of iteration like this, right? So we initially guess the solution this way, and then iterate. In the linear case, we have an obvious, in some sense, obvious iteration scheme from the equation, right? These are obvious iteration scheme, right? These are obvious iteration scheme. If we ignore SOR portion, as you can see, we can remove W everywhere. Then as you can see, these are all obvious. These relations come from the given equation, given system. This is obvious. So we need to find this kind of thing, for nonlinear system. So how can you find this kind of relation? And it comes from the Newton's idea. So how can you find x1, x2, xn equals something? So something, and this kind of relation came from, in this case, the given system, but in this case we cannot solve it for x1 because, as you can see, x1 and x1 are here, so we cannot directly solve for x1. Unlike linear system, it's not possible. Do you follow me? So Newton developed this kind of idea. We called this kind of equality f1 of x1, x2, xn, and then even the right hand side can be removed to create 0 on the right hand, right? So we can create this kind of equation, not necessarily linear, and then the second equation can be written the same way. And so on. So we have, for instance, n equations like this. So we should write the equation this way, and instead of writing these kind of things all the time, we create a vector function, capital F, having these functions. F of x1, x2, x3, xn equals f1 function, f2 function, fn function. So we write functions this way, and then we use Newton's idea. Newton's idea is this: at vector point, right? Instead of writing x point this way, we call this capital X, right? Capital X is a vector like this. So capital X equals f of x0, initial point like 1, 1, 1, 1, right? So we can call this x0, right? 1, 1, 1, 1 is x0. And then plus the derivative of this vector function, right? Vector function multiplied by x minus x0. And then more terms. So this is the Taylor series expansion style in vector form, right? In vector function, we have Taylor series expansion around the point, around the vector x0. Do you follow me or not?
What's in the square?
I will describe this thing later, but this square usually has, in one-dimensional function case, derivative. We have derivative in Taylor expansion, derivative, second derivative, third derivative. Taylor expansion has this function, zeroth derivative, first derivative, second derivative, and so on. And this is the vector value, vector function. So we should define this thing clearly, but roughly derivative comes here. And following terms. And if x and x0 are close, then this value squared will be close to 0. So we can do this kind of approximation, right? So this is the idea of Newton's method. So we should understand what we are doing here. Initially, to solve a system, we want some relation like this, right? We want some relation like this. x1 equals something, x2 equals something, x3 equals something. We want some relation like this. Then how can you get this kind of relation? The key is here. The key is from Taylor expansion of the vector function, right? This is a vector function. Then, because first the derivative of this kind of thing is calculated, some people just say derivative of f, like df, and I will use this notation. Jacobian of this function f. Jacobian of this function f at x0, right? At x0. So Jacobian of this function at x0. So the derivative in this case is Jacobian, and then Jacobian will be defined very soon. Any questions up to this point? Just Taylor expansion and Jacobian. So when you have function like f, capital F, then the Jacobian of f is defined this way. f1 differentiated with respect to x1, and then f1 differentiated with respect to x2, and so on, and then f1 differentiated with respect to xn. Similarly, f2 differentiated with respect to x1, and so on, and we write this kind of thing all the way down. This is the Jacobian function. So it's a function, and then once we have a function, we can have this kind of relation. F of x equals f of x0 plus f Jacobian of f at x0, x minus x0. Here, all the functions are vector-valued functions. These are all vectors. Then, what is our goal? Our goal is finding the solution, and then solution means finding something satisfying this, right? Solution means finding x satisfying this. This is our goal, right? Because of our goal, we will write this because it's our goal, right? We write this. Then, can you solve this with 0 for x? Can you solve this for x? So let's solve this for x. And what happens? If we solve this for x, then x minus x0 multiplied by Jacobian f x0 equals minus f x0, because it's 0, right? Because it's 0. And then we multiply both sides by the inverse matrix of the Jacobian, right? Inverse matrix of the Jacobian. So x minus x0 is the... So we multiply this thing on the left-hand side, right? So left-hand side is multiplied by the inverse. Inverse, and then minus this one, right? Minus this one. And then, finally, we can write x. So this is the relation that we can derive to solve the equation. So we eventually derive some relation that we can use to iterate. So in linear system, it's very obvious to find the relation. In nonlinear system, we must find something using this method called Newton's method. And this is very, very widely used in handling nonlinear systems. So I will solve one example with you. So this is, so you may make up a nonlinear system if you want. So what nonlinear system do you want? x1, and then what power do you want? Squared. And then what coefficient?
4.
And then plus or minus?
9.
And then 3 times x1, x2, and then x3 equals 6, or minus 6 equals 0, right? So I write it this way. Do you follow me? So I create an equality with 0. It's possible to write 6 here, but as I mentioned, it's good to use 0 on the right hand side. So similarly, we can create a system, right? x1 squared plus x2 squared plus x1, x3 minus 7 equals 0. And then x1 plus x2 plus x3 squared minus 10 equals 0. So assume that we have this kind of system with nonlinear terms. Then as I mentioned, we cannot get x1 is equal to something or x2 is equal to something directly. Right? So to do it, we should use these things. So I will pause and then you can check everything up to this point. So this is f1. So initially it doesn't have any name, but I attach these names. So this is my attachment. It's not given, but I'm just attaching it. I am attaching these things to the equation, right? The first equation has the name f1, second equation has the name f2, and so on. And then capital F1 is the vector function like this. Then Jacobian should be found. So let's find the Jacobian of this function. What is the Jacobian of f? Jacobian of f is what? If you differentiate the first function f1 with respect to x1, what do you get? If you differentiate this with respect to x1, then 4x1 and then minus 3x2. That's it, right? I mean 8x1 So do you follow me? I differentiated this function, f1, with respect to x1, right? f1 is differentiated in 8 times x1, and then 3 times x2, and then 0, 0. And then I can differentiate this with respect to x2 and x3. So do you follow me? So we differentiated the function f1 with respect to x1 and x2. So please do the remaining differentiation. So I completely determined the Jacobian function by differentiating f1, f2, f3 with respect to x1, x3. So I checked them and then everything looks good. Do you find any mistake or difference? Then let's apply the formula. X output equals X input minus Jacobian F, right? Jacobian of F calculated at X input, right? X input multiplied by, matrix multiplication by F of X input, right? So this is the formula Newton found, right? And then using this Newton's formula, we should iterate. So initially, we can guess this way. Oh, let's guess this way. x1, x2, x3, which is x, right? X or x0 is equal to, initially we say, oh, 1, 1, 1. So we guess the solution. Then, as you can see, x out equals 1, 1, 1 minus Jacobian with 1, 1, 1, right? Jacobian with 1, 1, 1. Then a minus 3, 5, minus 3 times 1, negative 3, and then 1, and then 0, and then 2 times 1, 2, and then 1, and then 0, 0, and then 2 times 1, 2. Inverse, right? Inverse. And then f of x0. So let's plug in f0, 1, 1, 1. So 1 replaces x1, 1 replaces x2, 1 replaces x3. So 4 minus 3 plus 1 minus 6. So total is what? What is the total? Negative 4, right? Negative 4. 1, 1, 1 gives us negative 4. Right? If you use 1, 1, 1 here, it will give us negative 4. And what is the next number? If you use 1, 1, 1, negative 4. And then if you use 1, 1, 1, then you will get negative 7. So this is what we get, right? Then it's not very difficult to find these things because computer calculates the inverse and then calculate the matrix multiplication and then subtract from 1, 1, 1. So eventually we'll have some number. Right? We eventually will have some number A, B, C, right? Then these A, B, C are used here, right? A, B, C are used here and then used in X, Y, Z, in X1, X2, X3 position to find the next set and the next set. We continue this. So this is Newton's method. So essentially, we are iterating. So essentially, in this chapter 4, we study about the system solving method, and then finding this kind of iteration was our major concern. Any questions? Excuse me? What is this part? Oh, I see. If we differentiate these things with respect to x1, right? Thank you. I made a mistake. Yeah. I don't know why I got these things, but let's check it. So if we differentiate with respect to x1, x1 plus x3, 1 plus x3, right? One plus x3, sorry for the mistake. And then x2 differentiation, and then if we differentiate this with respect to x1, x2, 1, 1. So I made mistakes like this, and then because of the change, we should change these numbers. In any case, this is the method that you can apply. And once these things are determined, you program this part, right? You program this part. Then your program will use any ABC here and then in the equation and so on to iterate, like the previous example. So a little bit tougher part is the involvement of the inverse, right? This part is a little bit tougher, but I don't ask you to program this matrix inverse on your own. You may call any inverse function. So, in summary, so this is the summary of this chapter. In summary, essentially what you do is this one. We want to determine the solution x1, x2, x3, and so on by iteration, right? Then this x should satisfy some kind of relation, and x is equal to some iteration that you can find. Is either linear, or Gauss-Seidel, or successive over relaxation, or Newton, right? So we find some kind of relation like this, and then what you do is this one. We start with any vector, right? Any legitimate vector like this, and then with this vector we iterate and find the next vector, right? And then using this vector we find the next vector, right? And so, right? So we eventually iterate and iterate to arrive at the solution. Any questions? Then now, suddenly, we will jump up to this point, almost in some sense, this kind of thing other than the Jacobian. In middle school, students know about systems, right? Especially linear systems. But now, we will handle a tougher level stuff called interpolation or approximation, differential equations. So these are the things that we will consider from this point on. So interpolation, usually interpolation in two-dimensional plane or interpolation in three-dimensional space can be considered. So in two-dimensional plane, we can say input, right? Input point, and then output, right? This is the input, and then this is output. And then input and output meets at this point, so we collect these things, right? So these are given. So usually 0.1, 0.2, 0.3, these are given. Then we find some function passing through these points is called interpolation, right? This kind of technique is called interpolation. In three-dimensional space is essentially the same. Essentially the same. We have 0.1, 0.2, 0.3. Then we find the function passing through these points, right? It could be a surface, not just a curve. In two-dimensional plane, we have just curve, but in three-dimensional case, we may have a function, surface function, right? P4 and so on. So we are handling these kind of things in the chapter, and if you have any questions about this idea, ask me. And P1 can be written in this form. Usually we use X here, and then Y here, then X1, and then Y1. And you use this kind of thing, X2, Y2. And then you use this thing, X3, Y3. Here, P1 is given this way. We have input X, input Y, right? Input X and input Y, and output Z, right? This is the output, and then these are input, right? So X1, X2, X1, Y1 are input, then Z1 is output, right? So point informations are given in these kinds of ways. So these are interpolation. And we will focus on two-dimensional interpolation, right? Two-dimensional. Later, you may apply these things in three-dimensional or higher dimensional cases. So let's forget about this 3D interpolation or 2D surface interpolation, right? Then there are methods to determine appropriate functions satisfying the condition. For instance, assume that x1, x2, x1, y1 and then xn, yn are given. Then there are many functions passing through these points. There are many functions. So we can impose conditions. For instance, let's consider 2 points. Then are there just one function or many functions passing through these 2 points? This function passed through these points. This function also passed through these points, and so on, right? There are infinitely many functions passing through the points. So we impose conditions. We impose conditions, and I will briefly show you the method, because the next one is in some sense very trivial. I will, instead of writing down, I will show you the page. So as you can see, there are some ways to determine the function passing through the points, and these kind of methods, so I will cover individual things. I will mention about Newton's divide differences, and then I will mention about spline functions, especially cubic spline functions, and B-spline functions. So I will mention about these three things first. There are infinitely many functions, but if we limit the order of the function, limit the order of the polynomial, right? Limit the order of the polynomial or degree of the polynomial. Then, for instance, limit the order to the smallest number possible, for instance 1. In other words, I want to find the first order function passing through 2 points. First order function is a line. Then I should find the function passing through these 2 points. Then there is only one line, right? It's unique, right? This function is unique. So once we impose conditions, we can get uniqueness. So what Newton did was this idea. He wanted to represent these things systematically. So how he did it, he called this f of x1, right? Because we don't know the function, but at least we know the value, right? We don't know what f is, right? But at least we know the value of f at x1 because it's given. So we call this fxn. Then with these things, Newton created nice representation. F of xi, xj is defined by Newton. So it's bracket notation, and this notation is given this way. F of xi minus f of xj, fxi minus xj. So he defined this thing. And he defined ijk thing. 3 things are used. and then it's like this. ij minus jk divided by xi minus xk. So he defined these kind of things. And as you can see, it's not very difficult to determine these numbers. And I will briefly show you how to do it soon. And then he defined these kind of things. So once we define these things, using these numbers, these are our numbers, right? Take a look. Is this a number or not? It's number, right? F of xi is a number. F of xi is a number given by the problem, right? So these are all numbers. Because these are all numbers, these kind of things are all numbers. Because these are all numbers, number, this is a number. So these are all numbers, right? These are all numbers. So using these numbers, he could find the function interpolating the given points. So to practice, you may pick 6 numbers. You may pick 6 numbers. So let me know your numbers. 6 numbers you pick. 1, 9, and then 2, 4, and then 3, and then what? I want to do hand calculation, so I will say like 8, right? So I pick 3 numbers like. So I chose these 3 numbers, and I want to interpolate. In other words, I want to find a function passing through these 3 points. And I want to impose a condition. The order of the polynomial should be 2, right? 2 or less, right? 2. So I impose a condition. Then what happens? First of all, I call this x1, I call this f of x1, right? I just label them. So, what is f of x1, x2? It is 9 minus 4 over 1 minus 2, and it is 5 over negative 1 or negative 5. Similarly, what is f of x2, x3? It is 4 minus 8 over 2 minus 3, negative 4 over negative 1, then it is 4. No questions? Then the next thing, what is f of x1, x2, x3? This is equal to what? Minus 5, minus 4, and then 1 minus 3 by the definition, right? Then this becomes negative 9. So negative 9 over negative 2 gives us 4.5. 4.5. So we derive these things. So we can calculate these kind of things no matter how many points are given. No matter how many points are given, we can find these things. Then what is Newton's idea? Newton's idea is using these things to find the polynomial passing through these points. And I will, instead of writing down the formula, I will give you the formula from the web. As you can see, what he found is a polynomial satisfying this. I used the 0-based index, but you may use 1-based index. Instead of 0, you may use 1, right? So this f part, and then x minus first node, right? And then with these things, and then these 2 things. So I will copy these things with, change the index. Instead of using given index, I will change the index. So by Newton, P sub 2 x polynomial equals f of x1 plus f of x1, x2 multiplied by x minus x1, and then f of x1, x2, x3 multiplied by x minus x1, x minus x2, right? So I just used one bigger index, right? One bigger index. I will show you both, right? So please compare it. I used one bigger index than the given one. Any questions? Then we are almost ready to finish. So let's do it. Then P sub 2 is what? Because of this region, f of x1 is what? What is f of x1? F of x1 is what? It's given by the problem. What is f of x1? 9. What is f of x1, x2? Negative 5, right? And then what is x1? 1, right? Plus, what is f of x1, x3? 4.5, right? And then x minus x1, x minus x2. Right? As you can see, we derive the polynomial. So instead of doing algebra, I will use computer to check the values. So I will define the function f. I will say p2 of x function is 9 plus minus 5 times x minus 1 plus 9 over 2 times x minus 1 times x minus 2. So I define the function p2, right? P2 function is defined. So what is p2 of x1 or 1? By the theory, we are interpolating. P2 of 1 should be what? 9. P2 of 2 is what? 4. P sub 2 of 3 is what? 8, right? Because we are interpolating. So I will check whether our function satisfies the condition or not. So what is this? Eight, right? So Newton's method interpolates the points. And if you have more points, you can do the same thing to find more, to find a bigger function or a higher order function. Please browse the idea and ask questions. So our goal was this kind of thing, right? Finding the function passing through the given points. In other words, if we plug in 1, you should get 9. If we plug in 2, then output 4. Plug in 3, then output 8. So our goal was doing this, and we did it. So this is Newton's divided difference method.
So this is not a curve fitting. It's a function that it's going to go through.
Go through each point. So it's not closed. When it is closed, then it is handled in approximation section. So it is interpolation thing, but in approximation, it is close to the points, then it's approximation. But it is really passing through the point in this case.
I understand. I guess I'm not understanding why people even use curve fitting and not use this technique.
Oh, you will see very soon. You will see. You will see the reason. Assume that we have very many points. We have very many points. Then our function order will grow, right? Our function order will grow. So I will give you a function like this, like such as P11 function, right? P11 of x.
I think you just answered my question.
So P11 function should have, like P2 function should have second order highest power, right? P11 order function should have 11th order power, right? And then something like this, right? 10th order function, and then something like this, right? So let's skip other parts. So something like this, right? Then let's plot this function from x running from minus 3 to 3. So it doesn't show very much. So let's reduce it to about 2. Still doesn't show very much. So my example isn't great, but when you use higher order function, the problem is this. Assume that we want to find the curve passing through these kind of points. And our hope is this. Oh, I want to find the function passing through these points in this way, right? This is our goal. But unfortunately, if you use just this kind of thing directly, then in many cases, sometimes this may happen, but in many cases, function may look like this. Right? The function may look like this. So like it is oscillating style. The mathematical definition of oscillation is different, but just intuitively it looks like oscillating function. So if we use higher and higher order functions, we have severe problem like this. So our goal was finding a function like this, but it doesn't achieve the goal. It just has this kind of complicated function.
The higher order functions will
have that kind of bad effect. So our goal was finding a function like this, but unfortunately, if we use higher order function, then it may oscillate like this, right? Not mathematical oscillation, but with intuitive oscillation. So because of this problem called Runge phenomenon or Runge-Murray phenomenon, we need to do something else. Why? Because our goal was fitting these things, right? In other words, I want to find the curve passing through these points. So somehow this passed through the points, but the pattern isn't great. So we want to have this kind of pattern instead of this kind of oscillating pattern. Because of this reason, we now want to study about splines, especially cubic splines.
Isn't that what we just did? We impose a restriction or a caveat or whatever on our problem and say, hey, I'm going to try a polynomial, I'm going to try a quadratic, I'm going to try a fifth order, and I'm going to see what it looks like. How do I know that I have the best? How do I know I don't have those changes in between the points?
So interpolation has no wiggle room. Interpolation should be exact, right? So if we use interpolation, then with imposed condition like passing through the given points, for instance, if we have 3 points, then second order function is imposed, right? Second order condition is imposed. If it has 4 points, third order. If we have 5 points, fourth order, sixth order, fifth.
Okay, so I impose the order depending on how many points.
Right. So we don't have any wiggle room here. But in approximation, we can have some kind of wiggle room that we can use. In other words, we want to impose the condition like third order all the time, or even linear regression style first order function or second order function.
Okay, so if I have, say, 8 points, and I say I'm only going to interpolate with a second order.
But then it generally is impossible. Interpolation should pass through the points. But if you
the only way to do that is with
seventh order function to have a unique polynomial. But if you use if you want a function closely passing through the points, not really passing, but closely passing the points, then you can impose the condition like first order or second order on your own. So interpolation has no wiggle room. So once number of points are given, then the order should be determined if we use polynomial. If you use something else, then something else should be imposed. So this is the situation. But now we do not like the phenomena like this, right? We do not like phenomena like this. So we want to define splines, and from this point on, we consider the splines. Splines are the function satisfying smooth derivative condition stuff, right? Very smooth looking, not mathematical smoothness, but intuitive smooth polynomial, right? Some polynomial that looks smooth. In other words, it should pass through the given points, right? It should pass through the given points, and then it should have same derivative, right? Same derivative. It should have same derivative, right? So the derivative should be the same, right? Or even second derivative should be the same. So these kind of conditions are imposed in splines. If we do not impose this condition, what happens is this. So as you can see, this function passed through these points, right? My function passed through these points, but as you can see here, the derivative has a problem, right? This is the derivative, and this is the derivative, right? And then this is the derivative, this is the slope, right? Slope, right? As you can see, slope are not the same, right? Slopes are not the same at the same point. So we impose the condition like first derivative should be the same, even the second derivative should be the same, and so on. Right? So by imposing the condition, we find the smooth looking polynomial.
If we use an interpolation scheme and we have 8 points, we're going to use a seventh order function to fit it.
Right.
If we do that, we're not going to have a problem like you're describing here.
Here means what? The top one or bottom? The oscillating one?
Yeah, I'm talking about the interpolation. If we use the interpolation scheme, we fit all the points, and we use a number of points -1 order, we're not going to have that problem.
So this problem you mean? Right.
We're not going to have that.
Right, but we have this problem. Higher order problem. So the order is too high, then higher order may fluctuate very rapidly. So because of this reason, to avoid these kind of problems, what people developed was finding function separately, piecewise polynomial is found. So we find the cubic polynomial inside this interval, right? So we find the cubic polynomial inside this interval. Similarly, we find the cubic polynomial inside this interval, and then we find the cubic polynomial inside this interval. Right? So we find the cubic polynomial in each interval, but it's not just free. It should match at this point, right? It should have the same height, and it should have the same slope, and it should have the same second derivative. So all these kind of things should be satisfied. Right? First derivative, right? Height should be the same. First derivative should be the same. Even second derivative should be the same. So even though these are separate pieces, like first piece, second piece, third piece, all pieces are cubic, right? Third order polynomial, right? Third order polynomial. it should satisfy the conditions, right? Slope should be the same, second derivative should be the same, slope should be second derivative. So this is what we want to do. So these are called splines. So
we only use a cubic because that will give us not only the derivative, but the second derivative, the kind of
right. More than that is not required in this case. Of course, you may consider fourth order or fifth order splines, but for what, right? So this is the goal. And there is a method doing it. And one method is finding second derivative at these kind of points, right? Second derivative at this point, say M1. So M1 is the second derivative. So call the spline function S. Then S second derivative at this point, x1 is M1. And then the second derivative at this point is M2, and so on, right? So we determine M1 and M2 and M3 and M4 and so on. And from this, we do the anti-differentiation to find the function, because by doing anti-differentiation twice, we can find S, right? Do you follow me? By doing anti-differentiation twice, we can find S. So this is the method, and the method is completely explained here. I will go to the formula instead of writing the formula on my own. So this is the situation. Assume that we have x1, x2, x3, x4, and so on. Then the distance is called hi, right? The distance between x1 and x2 is h1. Distance between x1, x2, and x3 is h2, and so on. And then we call the second derivative, right? We call the second derivative m1, m2, m3. Then these are still unknown because we don't know s, we don't know these numbers, right? So we determine these numbers with this condition. So we impose the condition and we determine these n-1 numbers by solving this linear system. It's not very difficult to solve this linear system. Once we solve this linear system, then m1 up to m-1 are determined. Then these numbers will be used to determine s in each individual interval. So these are the steps you can use to create spline. Then you will find a nice function passing through the given points. It doesn't oscillate. It doesn't look kink like this. You don't see kinks or cusps like this, right? You don't see cusps like this. Or it doesn't oscillate like this. You see some curves like this if you solve this. So I will pause, and then you may browse whether you completely understood these things or not. Our major goal is not this style. Our major goal is this plan that I will spend a lot of minutes or time, right? Please browse these things and ask questions. So to determine spline function in individual interval, right? In individual interval, we define spline function. We must solve this linear system for m1 up to m-1, and m represents second derivative at the nodes, right? Then, once we determine m1 up to m-1, we use m1 and these things to determine individual polynomial in individual interval, right? In individual subinterval.
Where is the integration taking place?
M1 and M2 are all numbers, right? From those numbers, we do the integration and integration to determine S. So as you can see, it didn't have these things, but now it has a lot of terms like cubic terms here because of the integration. Those steps are all skipped here because it requires about 2 hours of explanation. So what you see is the result, right? So you take a look initially. So let's use an example. So you may pick points. So I will pick interval like this, 1, 2, 3, 4, 5, right? Are these enough? Then you may pick heights. What height do you like? 2, and what heights? 3, what heights? 1, and then what height? 7, and then what heights? 5, right? So we choose these heights, right? So we want to find the polynomial, cubic polynomial inside this subinterval, right? And then inside the subinterval, and then inside the subinterval, and then inside the subinterval, right? So we want to find these kind of polynomials. How can you determine these things? So first of all, we should determine M1, M2, M3. And then M0 is 0. M4 is 0. So these two numbers are zeros. These two numbers are zeros. And we impose the condition M1, M2, M3. And then we don't know what M1, M2, M3 are. So we should determine M1, M2, M3. How can you determine it? We should solve a linear system. Right? We should solve a linear system. So once we solve a linear system, M1, M2, M3 are determined, right? Then using these numbers, using these M1, M2, M3, we generate the function. We generate the function S this way, right? In each individual interval, right? From x0 to x1 or x1 to x2, x2 to x3, x3 to x4, we determine this polynomial. And then we plot those things to have a function passing through the points. Then take a look. System has these things. H, in my case, H is 0 or H1, because it is zero-based index. You may add one more points, right? So you may add one more points here, right? 0, and then you can say 1, right? So we have, in fact, this interval 2. Then this has M0, this has M1, M2, M3, M4, and then this is M5, right? M5 is 0, and then M4 condition is lit. So we added one more points, then we have M4 here. So it doesn't matter. So you can just add as many points as you like. Then in any case, by solving this linear system, we can determine it, but I will show you how you determine these numbers. How you determine these numbers. So take a look. H0 is what? Between x0 and x1, what is the distance? Between x0 and x1, what is h? 1, right? What is h1? 1, right? So our h is 1. So h is 1. 1 plus 1 divided by 3. So 2/3 should be used here. 2/3, right? Do you follow me? And then, next one. H1 over 6. Right? And then next one. 0, 0. Not 0 here. It is 1, 6, right? Sorry. So I wrote down the left side by using this condition, right? So from the given condition, we can fill the matrix, right? You can fill in the entries. So if you don't understand, you can ask me. And the right-hand side, has what? y2 minus y1 over h1 minus y1 minus y0. Because of this reason, we can say y2, right, y2 minus y1. So I'm just copying these things. 3 minus 2 over 1 minus 2 minus 1 over 1. So I just copied this part, right? I copied this part. And then please find the second one. y3 minus y2, y2 minus y. So I wrote down the complete system, and if you have any questions up to this point, you can ask me. So we can solve this system for M1 through M4 using any method, right? Using iteration, LU decomposition, anything, right? Or you can even use your MATLAB or Maple built-in function. So M1, M2, M3, M4 are determined by solving this. Then the final step is what? The final step is using the number, right? M1, M2 are all numbers, right? These numbers are plugged in. These numbers are plugged in here, right? Like 1.6 could be plugged in, and then as you can see, we can determine S for the interval from x0 to x1, right? From x0 to x1, third order function is determined. Right? Because it's very straightforward, I don't want to cover this part at all, because it's straightforward, right? And then, for the interval x1 to x2, we can find the third order function. From x2 to x3, we can find the third order function, and so on. So from x0 to x5, we can sketch 5 different cubic order functions, right? 5 different cubic functions can be sketched from x0 to x5, from x0 to x1, x1 to x2, and so on. Then it's a split. So, any questions up to this point?
So basically what you're doing is you're matching the derivatives of the functions on either side of the function.
Right, especially second derivative, M2, right? So we are matching the second derivative. Then the next step is doing this way. It is possible to find the cubic order, cubic spline by solving system, right? So previously, cubic spline was found by solving this kind of system, and then by using S function in each interval, right? S function in each interval. This was the method that we studied. And now, in this course, instead of this method, we will learn about the spline. Basic spline, and the B spline is a fixed function. Usual spline has freedom. You can have any shape, right? Any cubic function satisfying the conditions. But B-splines are fixed functions. How do people define the spline? Roughly, this is the idea. Our center should have height 1. Our center should have height 1. And then, somewhere in between, it has smaller value that I will show you very soon. A little bit smaller value. And then at end point, it should be 0. So we define a function like this. And then the exact pattern will be shown very soon. So this is the B-spline, right? B-spline. And I will let you know the detailed form once you get the idea. Then what is the idea? Idea is this one. We define B-spline for some node 1, right? And then we define B-spline for node 2. Then what is the difference? Only shift, right? Only shift happened, right? Only we shift, and then shift, and shift, right? So only shift a little bit. B1 spline, B2 spline, no big difference, right? Only one unit shifted, right? And so same pattern all the time. Then to create a cubic spline or any spline, we just consider the linear combination of these things, linear combination of these splines, right? These basic splines are linearly combined together. Then all these looks very smooth, right? That means if we combine them, the combination will be smooth too. That is the goal. Then eventually we'll get a spline. So,
sure I understand what you mean by the shifting you were discussing.
So for instance, say that this is B1. Assume that this is B1 spline, right? Right? B2 spline has exactly the same shape, but this one is B2, right? And then B3 is has exactly the same shape, but it is shifted, right? And so, right? So if we look at just one spline at the center, B1 spline, B2 spline, B3, all the same. Shape is the same. Only difference is shift. For instance, sine x looks like this, right? Sine x looks like this, right? Sine x minus pi over 2 looks like this. So if we look at if we use the same initial starting point, then the shape is the same. The only difference between the two is the shift, right? Similarly, B1, B2, B3, any spline are the same, essentially, shape-wise. The only difference is the shift. Do you follow me? So by just knowing one B-spline, you know all the B-splines, right? I know it's one B-spline, you know all the... So I will show you the definition. Definition isn't very bad. As you can see, we define the spline this way. So this is the B-spline. BI, right? BI is centered at I, right? I. In other words, I want to call B1 to be the spline having the highest point at I. Do you follow me? Of course, these kind of thing can be defined anyway, but for convenience, I located the highest point at I. In other words, assume that this point is x5. This point is x5, and we use sequential nodes, right? x3, x6, x7. Then let's call this B5. Do you follow me? Because of this 5, I will call this x5. And what about the spline having 1 here? Then B4. What is the spline having 1 here? B3, right? And so on. So we define this kind of thing. And as you can see, or other place it has 0 height, right? Only between this sub-universe, it has something, right? It has something. So please browse these things and check whether you completely understand everything here or not. Any questions?
Why did you find the center spline d sub ix by equal 4? I'm not sure I understand why there was constants earlier.
What kind of concept?
Below the highlighted portion, you say by definition.
Oh, this part is not our major concern. Only explaining the heights. I said this thing. I said it has the top position here, right? It has top position. So roughly, if we measure the height, we want to have 4 here. And if we measure the height, we want to have 1 here, and 1 here, and then 0 here. And then all the way 0, 0. Just if you plug them in, then you can find the numbers. For instance, if you plug in xi minus 1, what happens? If you plug in x minus 1, what happens? 0, 0, 0, h cubed divided by h cubed, so it is 1, right? Do you follow me? If you plug in xi, what happens? xi minus, right? xi, what is x minus, what is xi minus x sub I minus 1? Hi, right? Right? H is the distance. H is the distance between the points. So H, right? So h cubed, h squared, 3 and minus cancelled out, and then h, and then 4h cubed divided by h cubed uses. Just examining the height. So this is the B-spline that we define. Of course, you may define differently, but B-spline is defined this way in the first place. So these are B-splines. So please browse these things and ask questions. Then as I mentioned before, once you have these splines, then creating a spline is a big problem. Why? By just attaching C1 and C2 and so on, we can create a spline. For instance, so after this, let's take a break. Assume that we want to define b minus 1. Then b minus 1 has height 4 here, right? b minus 1 has height 4, and then height 1 here. This is b minus 4. I cut the remaining portion, right? So this is b minus 4 spline. I mean b minus 1. I mean b minus 1 spline with height 4. And then this is B0 spline, right? And then this is B1 spline. And so, right? Then let's consider this portion. 2 minus 2b sub minus 1 plus 3b0 plus, what number do you like? Small number, 4b1, right? then as you can see, it's just a superposition of these functions, right? Minus 2 meaning, so I will, because these numbers are too big, it's difficult to sketch, so I will use 0.2, 0.3, 0.4, right? 0.2. Then I can shrink it. Then roughly 1/5 of this spline, 1/5 of this spline, right? 1/5 of this spline should be sketched. So this portion is this part, right? And then 0.3 times this spline is about reduced by this kind of amount, right? And then 4 times about this amount, right? So we create these kind of things, and then can you add these red curves? Then you can get some kind of curve, right? That is the spline. So I'm not good at sketching it, but at least we can try, right? So we add these things, and about this might be the height, right? About this might be the height. And then going down a little bit, and then going down a little bit. And then we are adding, and then about this point it is high, right? And then about this point it's about this. And then we are adding. So we may get some spline like this. So let's stop here, and then next time I'll continue. So let's, by this clock, let's resume at 3:11. So the idea is creating very nice function like this, and then using these functions by just linear combination, we can create a spline. That's the goal.
Can you go back and can you put the definition back up on the board there? Yeah, I'm not sure I understand what each one of the 5 lines are doing there.
I see. The function is defined in each subinterval like this. For instance, I will go back. For this subinterval, x minus 2, x minus 1, right? For this subinterval, we have this definition. And for this subinterval, we have this definition. And then for this subinterval, we have this definition. So it consists of 4 cubic curves and zeros. So good question. So this spline consists of 1, 2, 3, 4 functions and zeros. 4 functions and zeros. So this is this spline. For instance, say xi, right? And this is bi function. But as I mentioned, later people developed b-spline with other conditions and then create different things. But in this course, I used my book. 20 years ago, I learned this b-spline using a book. And this is the book definition, not the b-spline, but all b-spline defined in my book. So this red part, and then this, I don't see the color, some part, and the green part and the blue part are all defined by these small pieces, right? So this piece is the, I don't have a picture, red part, I guess, right? red part, right? This is the red part, and this is the next part, and this is the green part, and this is the blue part, right? And then 0 part is the black part, right? So we have these parts, right? Red part is defined by the first portion. Then as you can see, with this one, once you create b sub I for any I, with this one you can easily assemble these things to create a spline. That task is not required in this course, but if you are interested, you may learn. And the basic idea is this. Oh, it's nothing but just system solving. We initially want to know a spline passing through, for instance, x1, fx1, and then x2, fx2, and so on, right? So we initially have these points, right? Then you assemble these splines, right? B1, C1, B2, C2, and so on, right? And then determine C1, C2, and so on by using these conditions. This is nothing but just a linear system solved. By solving a linear system, you can determine C1 up to C something. Then by just using C1 up to C something with the spline function that you define, you can plot the spline, or you can calculate the value. So roughly this is it for the B-spline. But more important thing is not just sketching or implementing. More important thing is this one. Assume that you have a differential equation to solve. Right? Assume that you have a differential equation to solve. Then you assume that the solution is this one. Right? You assume the solution is this one. And then you plug this in here. Right? You plug this in here. And then by using weak form of these things, you create many equations, right? Many equalities. By using weak form, you create and then solve the system for C1 and C something, meaning your B-spline becomes the solution to the differential equation. So these kind of things will be studied later. So it's not just plotting, right? It's not just plotting or creating just cubic spline. Our focus is solving differential equation by assuming these things, right? By assuming these things. Then as you can see, it doesn't have many equations, just one equation, right? It doesn't have many equations. So what people do is creating a weak form. So usually this kind of thing with B-spline, right? B sub I x dx, right? Equals y b sub I x dx, right? So we create these things for each I, and then y, second derivative can be replaced by this thing, second derivative, and the y can be replaced by these things. Then bi and bj, right? bj here, sum of bj, and then we have a system. That kind of thing will be studied later. But roughly, this is our goal. So do you know what I mean? You want to find the solution to the differential equation. Then you want to use B-splines. Then what should you do? You create this kind of guess, right? Guess. You guess the solution using B-splines. And then plug in the B-spline. And then solve this weak form to generate many equations. And then solve this system of C1, C2, and so on. And determine C1 and C2 and so on, then you find the solution to the differential equation, and then you can even sketch the solution like this. So this is our major goal in this consideration of interpolation. So in my opinion, this spline is explained, and if you think you need more explanation or something you might doubt, then you can ask questions. So as I mentioned in this course, we are not very interested in plotting splines. There are many ways of plotting splines. We are more interested in the next step using these B-splines as basis functions, right? These B-splines form a basis. By using a basis, we want to generate, right? We want to span functions, especially solution. How? By determining C1 and C2 by solving weak form of the differential equation. So B-spline is done, essentially. And if you have a question, ask me. People, for convenience, say linear B-spline. Because of this term, in our usual concept, it is not even a spline, but linear B-spline is a spline like this. For instance, pick xi. So this is xi minus 1, and previous points here, and then this is xi, and then this is xi plus 1, and then more points, right? Then linear B-spline is a spline like this, and as you can see, it's not even a spline in our usual sense, but it's called the linear B-spline. And people use these things too, because it's very easy to determine derivatives and so on. What is the derivative of this? You can easily determine the derivative, right? So assume that this distance is h. Assume that this distance is h, and then this distance is also h, and then this height is 1, and then 0, right? So this height is 1 and 0, 0. Then what is the slope? The derivative of the, so let's call this phi function, right? So let's call this function phi sub I function. This is phi sub I function that I defined. Then phi sub I primed is equal to 0 up to this point, right? Up to this point, all the way up to xi minus 1, right? X sub I minus 1. And then at this point, the slope is over h, right? With xi minus 1 to xi. And then phi sub I derivative is what? Minus 1 over h from xi to xi plus 1. Derivative is 0 after xi. So linear spline is also used because it's convenient to determine derivatives and so on. And in fact, we will use these things to solve an equation using finite element method. We will use linear B-spline instead of cubic B-spline, because cubic B-spline has more functions, right? It's tougher to do these kind of calculations. It's possible. I'm not saying it's impossible, but these kind of things are necessary for more universe, right? Then it's tougher to calculate. So once I let you know how to solve differential equations using finite element method, using linear B-spline, you may practice these things with cubic B-spline. But I do not have time to cover them in the course, but at least I'm giving you the idea. Then with these things, it's very easy to interpolate. Assume that you are asked to interpolate these functions. What should you do? So I will let you know. 1, let's say 0 is x0, right? This is x0. And then you may pick any number. What number do you like?
1.
And then the next point is x1. What number do you like?
4.
And then the next point is this one. And what number do you like? And so on, right? So assume that you have these things. Then what is the combination, linear combination of the B-spline? Then 1 times phi 0, right? And then 4 times phi1, and then 9 times phi2 is the function interpolating these 3 points. Do you follow me? As linear splines, and then outside the 0, right? So for instance, -1, 0, and outside the 0, 0, 0 heights, right? 0 heights. Outside, like 3, 0, and the 0, 0 height. Then, as you can see, 0, 0 all the way up to this 0 point, and then I'm in -1, and then at point 0, 1, 2, and 3, at point 0 it should be 1, at point 1 it should be 4, at point 2 it should be 9, and then at point 3, 0. So it looks like this. Right? So it looks like this. So this is the linear interpolation. Linear interpolation means just connecting points by a line. So this concept is very, very important. Instead of individually solving everything and then plotting, we use basis function, right? We use basis functions like p set, right, or b set. And then using b sub I set or phi sub I set, we consider linear combination. And then it's not just plotting something. The key idea is using unknowns here, undetermined coefficients here, right? Undetermined coefficients here to solve differential equations by solving linear system of these undetermined coefficients. This is the key part. So in the future, I will mention it. So in the future, we'll try to solve differential equations like these. Then what you do is, using the solving the weak equation, for I, right? For I may run from 0 to n or something. So we solve these kind of equations. Then these kind of things create systems of C sub I, right? So these things create systems of C sub I, C sub 1, C sub 2, right? Then solve for C sub I, and then eventually assemble the solution. Solution equals C sub 1, phi 1, C sub 2, phi 2, and so on. So this is the idea. So interpolation itself is important, but the byproduct of interpolation, such as spline, is very, very important. So this is the end of B-spline, and I included the linear B-spline, even though there is no problem directly related to linear spline in this chapter, but in the future you will see these kind of B-splines. Then the next thing is using interpolation to multiply two big numbers. So assume that you are multiplying 1, 2, 3, and then 4, 5, 6. Then in your program, assume that you should really program everything. In other words, you cannot just take it for granted. You should multiply all these things and add these things. Then it's tough, right? Especially when the number is big, especially in coding. When we send messages, then we multiply numbers. Instead of sending the message like 0, 1, 1, 0, 0, 1, 1 directly, we multiply some number here, right? We multiply some number and send. then it's tougher, right? It's tougher to break. Even if you intercept, your number is scrambled. It's difficult to decode. Then let's consider this direction. 1, 2, 3 is nothing but 1 times 10 to the power of 2, and then 2 times 10 to the power of 1, and then 3 times 10 to the power of 0. So it can be written this way: 1 times x squared, 2 times x, and then 3 times 1. So this is the case. And then we call this function f function, right? F of x. So f of x is found, right? What is f of 10? What is f of 10? Thank you. F of 10 is 1, 2, 3. Then let's define g of x. Then 4x squared plus 5x plus 6. Then what is g of 10? So you are almost ready to multiply two big numbers. Then what is 1, 2, 3 times 4, 5, 6 in functional expression? F of 10 times g of 10. Or f of x, g of x calculated at value 10. So I will pause and then you can check out whether you follow everything up to this point or not.
I didn't like catch how does g of 10 equal 4, 5, 6?
So g of 10 gives us 4 times 10 squared plus 5 times 10 plus 6. So it's like this. Any other questions? Yeah. So let's do it. It's lucky to have maple. Without maple, it's difficult. But so f is 1x squared plus 2x plus 3. G is 4 times x squared plus 5 times x plus 6. So what is f of 10? What is g of 10? Right, thank you. It's obvious, right? Now, I will define one more function. So multiply, right? Multifunction, right? Multifunction is f of x times g of x, right? This is a multifunction, right? Then, what is multi of 10? So let's multiply this out. I multiplied two functions, f and g, and then plug in 10. So as functions, we could do these things, and if you have any questions up to this point, you can ask me. Yeah, that one will be explained later, but at least right now I'm explaining the idea. Then to multiply two functions, to multiply two numbers, to multiply we can multiply f of x and g of x, and then this part is important, and then use this substitution, right? Multiply the functions and then apply 10. That's it. So multiply f of x and g of x and then use 10. That's the check. But in any case, what is difficult part? You should know something is difficult. So what is the difficult part? Excuse me? I mean, theoretically, not even implementation. Theoretically, what is difficult part? Yeah, so you get the point. The difficult part is getting this one, right? Getting this one is difficult, right? One to 3 times 4, 5, 6 is difficult, right? Then what about multiplying f of x and g of x? It's difficult. F of x times g of x is difficult, right? Yes?
You don't really have to multiply the functions before you substitute the number in, right? You could substitute 10 in and
then it's the original problem. It's the original problem. There is no improvement then. Any other questions? Then what is the thing? Because this is difficult, what people think is this thing. Because this is difficult, how to simplify this step, or how to really find this multiplication without really multiplying them. How to find this function, right? A multi-function without really multiplying. Of course, my Maple could multiply them really as functions and then found it. But without really multiplying f of x and g of x, how can you find this result of function multiplication? So how can you find the multi-function, right? Let's use m instead of multi. So how can you find m of x? Then it's the original, almost the same as the original thing. Yeah. So there is no improvement. Right, then there is no big improvement. So this part is crucial. Why do I cover this thing in interpolation section? Interpolation should be used. In other words, m of x is interpolated, not m of x is interpolated, not multiplied. Do you know what I mean? So interpolate m of x. That's the idea. Interpolate m of x. Because this number is too big, let's use easier case. So I will show you how I interpolate the function. So instead of using 3-digit numbers, because I will do this in hand calculation instead of computer calculation, let's use easy numbers. So you may pick any 2-digit number for the first number and the second number. So one number multiply one number. Do you want to do 2-digit number? This way I can, excuse me? And then? 10 is 2, so I will change it to 70, right? So I will multiply these two numbers. Then, what is f function? F function is what? 2x plus 3. What is g function? x plus 7. Then I want to find the m function defined by the product of the two. Of course, I don't want to do direct multiplication. I want to interpolate m function. Right? I want to interpolate m function. Because the order of the function is 2, how many points are enough? 3-point multiplications are enough, right? 3-point multiplications are enough. I mean, 3-point interpolations are enough, right? Because the order, the result should be second order, right? Second order function requires 3 points. If you have a 10th order, you need 11 points, right? If you have 1 millionth order, then you have 1,000,001 point, right? Interpolation. Do you know what I mean? Then you may pick easiest point. I want to interpolation at 3 points. So you may pick any 3 points of your choice. What 3 points do you like? Use 0 or use 0. At 0, I want to interpolate, right? And then what number would you like? 1 and then negative 1, right? I chose these 3 points because these are easiest points. 0, 1, negative 1. Do you follow me or not? So I want to interpolate m function at these 3 points, right? What is the result of m at 0? F of 0 multiplied by g of 0, right? At 0, it is f of 0 multiplied by g of 0. Similarly, at 1, f of 1 multiplied by definition, right? This is by definition. And then at this point, f of negative 1 and g of negative 1. Then the numbers are found. 0, 0 gives us 21. 1, 1 gives us 40. And then minus 1. 6. Right? So we should find the function interpolating these 3 points. Then by using Newton's divide differences or something you can find. So please use Newton's divide difference to practice find the interpolating function of these 3 points. Interpolation function of these 3 points. Second order function. Newton's divide difference. I'm intentionally using this method even though there are better methods. So after finding m, use 0, because our goal was finding m of 10, right? Use 10. So after finding m function, use 0, because our goal was what? What was our goal? Our goal was m of 10 was our goal, right? We want to multiply f of 10 and g of 10. That is m of 10. So after finding m, use 10. So I did all the steps, right? First of all, I interpolated the function using Newton's method. And then after interpolating the function, I found the function like this, and then I use m of 10 to determine the number. That number is nothing but the product of the two numbers. So this is it. So please browse this idea and ask questions. So assume that you multiply 1 million digit number and 1 million digit number. Then usual multiplication requires each digit times 1 million numbers, and so, right? So 1 million times 1 million numbers should be multiplied and added together. If you use interpolation, you interpolate at 100 million and 1 points. And then you plug in 10. Then that's, oh, excuse me, sorry.
But to get each one of your 100 million and 1 point, you need to do 2 multiplications, right? So you need to do an evaluation and a multiplication.
That multiplication is straightforward multiplication, right? Straight one multiplication step. That means 1 million, 1 billion and 1 million. I mean, you are right. 2 million and 1, right? 2 million and 1. So if you completely understand these things, then I will continue covering FFT and combine this thing with FFT. But if you have still questions about this, ask me. So we are not really multiplying two functions. We are interpolating at various points. Did I even use 10 in the interpolation? Did I use 10 or not? In the interpolation, right? Initially, f of 10, g of 10 was our goal, right? F of 10 and g of 10 were our goal, but we didn't even consider 10 here. We just picked convenient points, like 0, negative 1, and 1. We chose convenient instead of 10 to interpolate. After interpolation is done, we use 10 to determine the number. So m is found, right? This is m. This function is m. And then m of 10 is nothing but the function f of 10 multiplied by g of 10. And this is very, very important in coding, because in coding, people use big numbers, and the big numbers are multiplied together. Then we should do these things fast. Like, assume that you are multiplying 1 million digit numbers. Then if you program it using the method that you did in homework, it will take a long time, because 1 million times 1 million multiplication should be done. But if you use these things, it's linear. It's not n squared term. So this is the idea.
How many multiplications does the computer do if it uses this?
Like this. Assume that you are multiplying. I will show you an example. Right? Assume that you have these things. Then you have 9th order function, right? And then another function is 9th order function, right? So 9th order function multiplied by 9th order function gives us 18th order function. Then you need to pick 19 points, right? 0, 1, negative 1, and so on, right? You need to pick 9 points randomly. It's not necessarily this points, just 19 points randomly, right? 19 points of your choice. So you should multiply the values at 19 points. So total 19 multiplication will give you enough information. Instead of, if you use usual multiplication, right? If you use usual multiplication, then how many multiplications is required? 9 times 9, total 81 multiplication. So instead of 81 multiplication, we use just 19 multiplication. The major idea is interpolation, right? So we find m of x not by multiplying two functions, but by interpolation we find m of x. Do you completely follow me? Yes?
So we have to evaluate the function at each of those.
These chosen points, right?
Right, so we have to substitute that in and evaluate the y value of
Yes,
our
right.
coordinate.
Right.
Okay, so then that's better than
Yeah.
just multiplying?
When we multiply a few numbers, small size numbers, it is in some sense cumbersome, but I will go to the next case. Usually, when you design a chip, the multiplication is not done in decimal, it's done in binary, right? So there are a lot of binary numbers, and then these binary numbers are all multiplied together to determine something. But when you use these things, we do things in that pattern. The save is huge when n is large, right? When n is large. The number of digits that we need to multiply is large, is good. But when the number is small, it's not. So this is used in high-level coding, right? High-level coding. So I will summarize it. Instead of finding f of 10 multiplied by g of 10, right? Instead of finding it, we find f of x multiplied by g of x function, m of x, and then we interpolate m of x, right? At appropriate number of points, right? And then after interpolating the function, we use m of 10 to determine, and the base doesn't have to be 10. I use the base 10, but base can be 1,000 or any number. The base shouldn't have to be just 10. Base could be 1,000, 1,000,000, any number. So when I assigned this homework about 2 years ago, I asked the student to use base 1,000. In other words, 1, 2, 3, 4, 5, 6, 7, 8, 9 is equal to 1, 2, 3 times x squared plus 4, 5, 6 times x plus 7, 8, 9, right? The cubic order function. Then you can determine the next function and then interpolate at how many points? Second order function multiply second order function. So at 5 points you interpolate, right? At 5 points. And then do you follow me or not? So if you need to multiply this by 1, 1, 1, 2, 2, 2 something, then you multiply second order function by second order function. First order function is the result. So you interpolate this function at 5 points. Right? At 5 points you interpolate the function and then determine the result by using 1,000 later. Let's call this F. Let's call this G. Right? Then M of x equals F of x multiplied by G of x. Then interpolate at 0 something, and then 1 something, and then 2 something, and so on, right? So we interpolate at 5 points like these. Then we can find the function m of x by this interpolation. First order function is found after this interpolation. Afterwards, after m is found, we find m of 100. That is f of 100 multiplied g of 100, meaning 1, 2, 3 something multiplied by 1, 1, 1 something. So this is there. So please browse these things and ask questions.
Or 1,000.
Thank you. So we are not finding that kind of value. We are finding m of 1,000. So about 1 million might be okay. Most computers, in the past, computers had 16-bit integer in the past, right? So let's use Maple. In the past, our integer limitation was 2 to the power of 16. So if we passes this thing, even if we use unsigned, it becomes like 0 or something, right? It's a group, right? Cyclic group. In the past. But now, most computers use 32-bit numbers. Then you approximately use how many digits to represent a number? About 4 or 5, right? 4 or 5 digits. To be safe, about 4 digits, right? So 10,000 can be used. If you need to create some kind of package to do multiplication, then you can break up into 4 digits, right? 4 digits. Base is on 10,000 because it can handle 4 digits multiplied by 4 digits, right? 5 digits is too much, right? Sometimes unlucky thing happens. Then overflow will jeopardize the result. So what I mean is this one. As far as 4-digit numbers are multiplied, the integer result is exactly correct, right? Because it doesn't go to floating point calculation, just integer multiplied by integer. That is an integer. Then you break up the number into this kind of part, right? Assume that you are asked to, so assume that you need to multiply this number by this number, 8-digit number by 8-digit number. Then the easiest choice is this one. You represent this number by and you represent this number by, right? Then you have first order function multiplied by first order function and second order function. Then how many points you need to interpolate? 3 points, right? Because the second order function, 3 points, you interpolate at 3 points. After interpolating at 3 points, right? After interpolating at 3 points, you multiply, you plug in 10,000. So you can use your C language or something to do any large number multiplication this kind of way. So 3 digits is okay, 4 digits are also okay too, right? 3 digits is intuitive. You can directly use commas to represent a number, right? But it's not bad to use 4 digits. In Asia, people use 4-digit comma system. we don't really use comma, but in the numbering, we use 4 digits. Sometimes I'm very confused because I have 4-digit consideration and I should convert it to 3 digits, and I'm confused. Like I say many times, oh, $10,000 to mean $100,000, because in our system 10,000 means not necessarily 1,000, but 10 something means something like this, because we use 4-digit comma system. So people laugh at me because I meant 100,000 while I was saying 10,000. The same situation, right? 4-digit comma system. So any questions about the theory part? Or if you still have doubts, you can ask me. If you do not understand, ask me. So, final summary, we break up to we make a function from the given number, and then we interpolate the product, right? Not really multiplying two numbers, but interpolate the product. And then, using the product, you plug in the base to determine the number. That's the thing. Then the next thing is combination of these things with FFT. So FFT is the next part. Somehow, using polynomial isn't necessarily easy. Isn't necessarily easy. So as you practiced before, even interpolating polynomial passing through 3 points isn't necessarily easy. So what people consider is using periodic polynomials such as sine or cosine, right? Sine, let's use pi x, right? Or n pi x. Then it's periodic, right? It's periodic. Or 2 times n pi x, doesn't matter. This kind of thing. So if you use periodic functions, then interpolation is nothing but the determination of coefficients in front of sine or cosine, right? So sine Sn represent the coefficients for sine part, and then Cn represent the coefficients for cosine function, right? And then we can add these things. We can add these things from n0 to some number, right? Capital N. When n is equal to 0, this is 0, right? This is 0. So we can consider this kind of interpolation, right? So in this interpolation, we have unknowns at only these positions, right? At these positions. We have unknowns at these positions. If we interpolate a function using these things. So any questions up to this point? So assume that we are interpolating something, some points, then we find appropriate Sn set and Cn set, right? Sn set and Cn set to assemble a function later. So this is the idea of Fourier transformation, and using Fourier transformation we can determine Sn and Cn. So do you follow me? Completely follow me? So determining Sn and Cn is enough to determine a function, right? Once Cn and Sn are determined, function is created. Then it's good to use complex numbers, right? It's good to use complex numbers because if we attach I here, then Cn can also attach, have I, and these are all included then. With these things, we can use just one function, one complex number with e to the power of I n x or something, right? It's possible to use Euler notation to represent a function. So we are very close to FFT. Then I will show you the formula because I already explained the idea and I will show you the formula. Right here. So we can assemble the function later by doing this. By doing this, we can assemble the function later. So I used n instead of k, right? Here I used k, right? So after determining an, we can assemble the function by just doing this. Then how to determine ak? By using FFT, we can determine ak. So we have 10 more minutes, so I will show you how to determine ak. So let's go back. So for convenience, it divides it by this kind of thing. And let's return back to the stuff. And it starts at 1, right? It starts at 1. So I will change my index system from 0 to n minus 1. I will make it the same, right? From 0 to n minus 1. Repetition. So this is it. So after determining the combination of sine and cosine coefficient, say an, we can assemble a function, and this interpolates. This function is the interpolation function, say p, say f of x, right? So we can find the interpolating function this way. Because this course is not numerical analysis, I don't want to go too deep to cover the integral and all stuff. How to find an? Use FFT built-in function. So there is a built-in function to determine these things, and I will explain the details. There are two different courses in this college. We have full numerical analysis course, and we have this course. In this course, we focus more on computational part, not theoretical. In numerical analysis, we cover both, but we focus on theory part. Then I will show you how to do it. We usually assume this kind of evenly divided space. Evenly divided, instead of randomly divided space, evenly divided space. And then say x1, x2, x3, and so on, right? And so on. Then at we have A1, height A1, height A2, height A3, and so on, right? So we have heights. Then from these things we can determine capital A1 related to these things, right? And then A2 related to these things, and so on, right? And let's do it. I completely forgot how to run FFT on Maple. So I should say array. I didn't say array. That was the reason why it complains. So what I did was using packaging. Maple package, MATLAB package might be a little bit different, but the key idea is this one. Because these are all assumed, we don't even care about these things. These are all assumed. What we do is converting this set of number, A1, A2, A3, right? This set of number into this kind of set, right? Capital A1, A2, A3. In complex number. So MATLAB handles this better way, right? Instead of Maple style real vector and imaginary vector and later combining and then. So I want you to pick anything that you find convenient. So by using these things, I did the FFT, and I will write the result. Important thing is the result. So what I did was this one. 1 plus 0i, 2 plus 0i, 3 plus 0i, 4 plus 0i is interpolated. Right? This is interpolated. I'm FFT. So I FFT this thing. Then the result is 10 plus 0i and minus 2 plus 2i and the next thing is minus 2 plus 0i and finally minus 2 minus 2i. So this is called FFT. The exact formula is not our major concern in the course. So I explained the rough idea. We need to determine coefficients in front of sine and cosine, or in general, exponential function with Euler notation. So we need to determine the coefficient of e to the power of some function, right? And then the coefficient determination is done by FFT. Then from this set of points, we determine these coefficients in front of e to the power of something. So this is the idea. And the reverse of this step is called IFFT. Reverse of this step is called IFFT. Because we don't have enough time, I'll briefly mention about the connection of this thing with the multiplication of two numbers, but next time I will cover more details. Roughly, this is the idea. Usually, f of x multiplied by g of x called m of x, interpolation is tough, right? Usually m of x interpolation is tough. So we, instead of using general numbers, we pick this interpolation. In other words, we FFT f, right? We FFT g to determine the FFT of m by multiplication, right? And then later, we inverse FFT this cell, but this is too much, so let's stop at this point, and next time I will mention about the details of these things to do this multiplication. But FFT itself isn't for multiplication. We chose FFT to do interpolation and then IFFT, so assembling of functions.